students, as we are talking about important questions from solution chapter, today's important questions, that is define the term osmosis, osmotic pressure, and day-to-day regular life we are utilizing that osmotic pressure, that is application based question and the related sums. Yes, let us go and analyze all these points. First and foremost, osmosis. Osmosis is nothing. Actually, imagine lower concentration point, a higher concentration point. So, the molecules flow from lower concentration, passes through the semi-permeable membrane to higher concentration solution. Okay, now here come to this point. The flow of solvent from solvent into solution through semi-permeable membrane, it's called osmosis. Okay, now solvent, when we are talking about solvent, the concentration will be nil. Water molecules. Okay, imagine. The same way solution, if you take, concentration will be higher. Okay, now you just take a container. In this container, this is a semi-permeable membrane. Semi-permeable membrane means there is a small porous into that. So the molecules flow. It is acts as a filter. So this is a semi-permeable membrane. Okay, now this part it is a solution and this part it is a solvent. Okay, so the solvent molecules at concentration will be less. That means lower. Whereas solution part, the solvent and solute, both combined together, so naturally concentration part will be higher. So the flow of water molecules from solvent into solution, that means from lower concentration to higher concentration, it passes through semi-permeable membrane. It's called osmosis. Hope you got a better idea. What do you mean by osmosis? Now, next point we are talking about osmotic pressure. So, osmotic pressure, it is nothing, just to the opposite of osmosis. Okay, let us consider with this a small example. The same container we have taken. In this container, first part it is a solvent particle. Solvent, that means the concentration will be lower, and here this is a solution part. Okay, now it passes through what it is separated by semi permeable membrane. Okay, now the concentration part will be higher, this concentration part will be lower. Okay, now what we are doing for the osmotic pressure, the excess pressure applied on the solution side. Now this is a piston. Imagine we are giving pressure to the solution side. Why we are giving pressure to the solution side? In order to prevent the flow of solvent molecules from solvent into solution. That is osmotic pressure. See, osmotic pressure of a solution is defined as that excess pressure should be applied on the solution side in order to prevent the solvent molecules from solvent into solution. So generally from lower concentration to higher concentration only molecules are flowing. So to avoid this, we are giving excess pressure. So that excess pressure, it is called osmotic pressure. Hope you got a better idea. Okay, now when the solvent and the solution are separated by what it is, semi-permeable membrane. So semi-permeable membrane, it acts as a filter. You know very well, biology students, you know very well what it is, semi-permeable membrane. Hope you got a better idea about these two. Okay, now this osmotic pressure denoted by pi. What do you mean by pi? See here, want of observed that ideal gas. What do you mean by ideal gas equation? PV equal to nRT, right? The same way that pressure, instead of this, osmotic pressure he has taken. So pi V equal to nRT. Why he has taken this formula? Because this osmotic pressure acts as an ideal gas equation. That is what he has taken that equation. So what have observed this point for the dilute solution. Okay, so pi V equal to nRT. So n is what it is, number of molecules. So number of molecules, how do we identify? Given mass by molecular mass. Can we write it WB by MB? Okay, so for osmotic pressure, pi instead of P, we are using pi. Pi, it is what it is, osmotic pressure. P just ordinary pressure. PV equal to nRT. It obeys ideal gas equation. The same way pi VRT. What it is called? Pi V equal to nRT. So pi it is nothing. What it is? Osmotic pressure. Pi equal to N by V RT. So N by V, actually it starts with the concentration. Concentration. Concentration, we are talking about molarity. Molarity. Okay, so we can put it capital C. So pi equal to CRT. Okay, we can utilize this formula also for solving sums related to that osmotic pressure. Okay, another one more. PV equal to nRT. So instead of P, we can use what it is? Pi. I just mentioned, no. So pi V equal to nRT. Okay, N it is what it is? N equal to number of moles. So number of moles, it is given mass by molecular mass, no? So that is WB by MB. So let us apply this. Pi V equal to WB by MB into RT. So pi equal to WB into RT divided by MB into V. Okay, this V has gone there. Okay, now how to identify molecular mass of the solute? MB equal to WB, that is given mass of the solute, into RT divided by pi V. Okay, V, it's a volume of the solution. Hope you got a better idea about this point, right? WB, B it is a solute, A it is a solvent. You know very well, that is a fundamental idea about that. Hope you got a better clarity about that osmotic pressure. Related sums while solving, we can utilize this formula as well as this formula. Okay, now let us go and identify that day to day regular life we are using what it is, osmotic pressure, that is a reverse osmosis we are using for filter water. We are drinking water, no? So that is RO water we usually says. Okay, so that is RO water is nothing, reverse osmosis. Okay, now let us go and identify how it's working out, and finally we'll go for that solving sum related to this point. Okay, now, before going for reverse osmosis, which is very important, that is isotonic, hypertonic, hypotonic solution. That one I'll just discuss because this is very important for both point. Okay, now isotonic solution having a same osmotic pressure at a given temperature. That is isotonic solution. Okay, solution of equimolar concentration have the same osmotic pressure at a given temperature. It's called what it is? Isotonic solution. Same concentration, that is equimolar concentration, have the same osmotic pressure. That is called isotonic. Now, hypertonic, hypotonic. Hypertension, we are telling now like that. Hypotonic, higher value. Hypotonic, lower value. See, come to this point. The solution which has higher osmotic pressure than that of a given solution, that is hypertonic solution. A solution which has lower osmotic pressure. See, lower osmotic pressure, higher osmotic pressure than that of a given solution. That is called what it is? Hypotonic solution. Now, here finally we are coming to the conclusion. The concentration of hypertonic solution is more and hypotonic solution is less as compared to the concentration of the solution. So, due to the concentration only, we can identify whether it is a hypertonic solution or hypotonic solution. We can identify. Hope you got a clear idea about hypertonic, hypotonic, isotonic solution. Got it? Okay, now let us go and identify RO water, RO process, that is reverse osmosis. Now, reverse osmosis. How it's happening that reverse osmosis? The process of osmosis can be reversed if a pressure is larger than that of the osmotic pressure. Pressure is larger than that of the osmotic pressure is applied on the solutions. That is called what it is? Reverse osmosis. Come on, let us go and identify very clearly. Okay, osmosis you know very well. So this is the container, and here in the middle point what it is? Semi-permeable membrane. This is solvent molecule and this is solution. Okay, so what happened? That flow of solvent molecules from solvent to solution, the solvent to solution, it passes through semi-permeable membrane. So that is called what it is? Osmosis. Okay, but here reverse osmosis means the same idea only. Semi-permeable membrane, right? Okay, now in this point here, solvent and this is solution. So the concentration will be higher. Of course, this point also concentration will be higher. In this concentration will be lower. So the concentration from lower to higher it passes. So that is called osmosis. But here, just to the opposite. Now what happened? We are giving pressure. How much we are giving pressure? Larger than that of the osmotic pressure. So already we are giving pressure. Osmotic pressure is we are giving pressure on the solution side. So naturally the solvent molecules from the solution to solvent it passes. But still here the pressure larger than that of the osmotic pressure, that is reverse osmosis. Reverse osmosis. Okay, so reverse osmosis, how what happened here? So the concentration will be higher. So the concentration from higher location to lower location it passes. But here from lower to higher. So the molecules from higher concentration to lower concentration here passes. So that is called reverse osmosis. So here seawater desalination takes place through this process only. So our filter water also RO water we are telling no. RO water also gets from reverse osmosis. What do you mean by reverse osmosis? Here the process of osmosis can be reversed, that is pressure is larger than that of the osmotic pressure. Osmotic pressure we are giving, but still larger pressure we are giving through which side? Solution side, that is a concentration higher side we are giving. So naturally you are getting RO water, pure water you are getting. Hope you got a clear idea about RO water. Now let us go through that osmotic pressure related sums. Okay, 2.00 centimeter cube of aqueous solution of protein contains 1.26 gram of protein. The osmotic pressure of the solution at 300 Kelvin is found to be 2.57 into 10 to the power of minus 3. But calculate the molar mass of the solution. Okay, just now we have gone through that formula, right? Osmotic pressure formula. What is that formula? I hope you got an idea. So pi V equal to nRT. So pi, it is actually osmotic pressure. Okay. So pi V equal to N, it is what it is, given mass, that is number of moles, given mass by molecular mass. Okay, let us apply this. WB by MB into RT. Okay. Now pi equal to WB by MB into RT by V. So MB only we need, right? Okay, MB equal to WB by pi into RT by V. Right? Now let us apply all the values. What is it? Pi value 2.57 into 10 to the power of minus 3 bar, and WB how much? 1.26 gram, and V how much? 2.00 centimeter cube, and temperature 300 K. MB we have to identify. MB actually we have to identify, and RT, right? So R equal to, that is a constant, right? 0.083 bar Kelvin inverse mole inverse, right? Okay. Now let us apply the value. MB, how much, what it is? MB here, MB only we have to identify, right? Now next one, what it is? MB equal to WB, what it is? What is it? WB 1.26 into R 0.83 into T 300 Kelvin divided by pi. What is the value of pi? 2.57 into 10 to the power of minus 3 into V. We just turn into liter. So 0.2. So what is the answer? You will get it. Come on, let us go for it. 61.039 gram per mole. Why I mentioned gram per mole? Do you know that? This is MB, right? What is that MB full form? Molecular mass. So molecular mass, naturally you will get gram per mole. If you know this formula, this comes from where? PV equal to nRT, ideal gas equation. That is the guru of ideal gas equation, because it obeys all the ideal gas solutions. Okay, now ideal solution and ideal gas also. Hope you understand all these points. How do we get it? And elevation of boiling point, depression of freezing point, that is also we are requiring all these ideas. Hope you got a clear idea. Whichever question comes, I hope you are able to analyze this, and you just apply the values. For applying values also you will get some marks. Okay, so please understand the question. What is that question? You just read out. From that reading only you will come to know that clarity. Then you will apply the formula. When you are applying the formula, you will come to know what is the requirement. From that you will do. I hope you got a clear idea. Okay, now we are going to see the abnormal molecular mass. Let us finish this chapter. Now let us go and analyze the abnormal molecular mass. This is very interesting and simple. From there you will get, definitely you will get two questions or one more question. Okay, now in the abnormal molecular mass, what is the conditions to be applied? Conditions of accurate molecular mass of the solute. First and foremost, the solution should be dilute. Why the solution should be dilute? So the molecule of that solute particle easy to associate as well as dissociate. So it is easy to agitate. See, solution should be dilute. In the concentrated solution, the solute particles can be interact with one another and for the agitates. Right. The solute particles neither associate nor dissociate into that solution. See, generally, colligative property means it depends on the number of particles, not on the nature of particles. Already I mentioned the same idea only here also. So the number of particles in the solution, since colligative property depends on the number of particles in that solution only, not on the nature of the solute particle. So molar mass determined on the basis of colligative property. So molar mass of the solute depends on the colligative property. So abnormal molecular mass in dissociation into the solution. Here two main points you have to consider. So first and foremost, molar mass of the solute is inversely proportional to the colligative property. This is very important point to be noted. Why? Because this will help you to solve the sum. Okay, molar mass of the solute is inversely proportional to the colligative property, and observed molecular mass will be half of the theoretical value. Half of the theoretical value. Okay, let us go and analyze with some example. Now, suppose if you are taking the substance we can divide it into two parts, that is substance divided into two parts according to this. To explain here, electrolyte and non-electrolyte. Okay, now electrolyte means it is completely associate and dissociate. This is substance. Electrolyte substance means it will be associate 100%. It will be associate and dissociate, right? Dissociate, right? But here non-electrolyte means 100%. It will not associate, neither dissociate. Okay, we can give one example of electrolyte and non-electrolyte. Now, for example, NaCl and MgCl2 and Al2SO4 thrice. So these are all electrolyte. So it will be associate as well as dissociate. Whereas non-electrolyte, for example, sucrose, glucose, and fructose. So these are all neither associate nor dissociate. Right? Okay. Now let us go and identify. These are the substance with dissociate. NaCl. It gives Na plus Cl minus. The same way MgCl2. It gives Mg2 plus Cl minus. The same way Al2SO4 thrice. It gives 2Al3 plus SO4 2 minus. 3 SO4 2 minus. Okay, now here number of particles increase. Naturally, colligative properties also increases. So, observed colligative property, if we consider that observed colligative property divided by theoretical colligative property, so this point only want of introduced. So, what here, want of factor account for the extent of association or dissociation. I equal to normal molar mass divided by observed molar mass. In the same way, observed colligative property divided by theoretical, that is normal colligative property. Finally, we are accomplishing with that total number of particle after association or dissociation divided by number of particles before dissociation or association. With this one small example, already we have gone through that. NaCl, it gives Na plus Cl minus. Okay, now this is total number of particles after dissociation or association. After dissociation or association, how much it is? 2 divided by 1. Before dissociation or association. The same way here. So naturally what you will get I factor, it is 2. Mg2 plus MgCl2. You will get Mg2 plus Cl minus. So naturally you will get what it is? 3. How you will get 3? Here 2 and here 1. So 3 divided by 1. So how do you get 3 divided by 1? Total number of particles after dissociation or association divided by number of particles before dissociation or association. Now the same way, Al2, SO4 thrice. How you will get for dissociation? Al3 plus 2Al3 plus and SO4 2 minus 3. SO4 2 minus. So naturally how much? 2 plus 3. I factor it is 5. How do you get 5? So here 5. Here 2 plus 3 5 and here I factor what it is? Total number of particles after dissociation. This is after dissociation. This is before dissociation. So after dissociation this is 5 divided by 1. This is 1 only. Right? Okay. Hope you got a better idea. Now let us go and analyze what is it weak electrolyte and what is it strong electrolyte before association and before dissociation. All these ideas let us go and analyze very clearly. And one more example also we can go for it here. K4FeCN6. K4FeCN6. Okay, now number of times I factor they are asking this also. So this is what it is when it is dissociative. This is K plus. How much K plus? 4K plus FeCN6. Okay, now this is 4 minus. Now here this is minus 1 and this is plus 1. Okay, now altogether it is 4 and this is 1. So altogether 5. So I factor it is 5. I factor for K4FeCN6 it is 5. So they may ask in board such kind of these questions. Hope you got a clear idea about. See, dissociation, number of particles are important. See, generally colligative property, what it has mentioned, number of particles only, not the nature of particle. The same way here also that. Now for example, association. Suppose if we go for association, now dissociation we have gone through. Association means now here CH3 COOH plus CH3 COOH. Now combine together CH3 COOH twice. So this is what it is, association. So here want of factor, what it is? Want of factor, it is decreases as the colligative property decreases. Number of particles decreases. Colligative properties also decreases. As the number of particles increases, colligative properties also increases. As the number of particles decreases, colligative properties also decreases. Hope you got a clear idea. Come on, let us go for the association and dissociation very clearly. Now let us channelize the way association and dissociation very clearly for the formula's sake. To understand this formula, let us go for the n mole of A. It gives AN. So n mole, it gives 1 mole. So therefore 1 mole, it gives how much? That is the matter. Okay, now here to identify, so n mole it gives 1 mole. So 1 mole it gives how much? Cross multiplication 1 into 1 by n. Okay, now degree of dissociation point if we are taking means here alpha, here minus alpha, here you will get plus alpha. Why? Because after reaction completely it transferred. So here, how can we write a total degree of dissociation? 1 minus alpha. Here what it is? 1 by n alpha. How do we get 1 by n alpha? Here 1 into 1 divided by n. How do we get 1 into 1 divided? N mole give 1 mole. So 1 mole give how much? So 1 into 1 divided by n. So it is 1 by n alpha. So total degree of dissociation, how do we identify? Here 1 minus alpha plus 1 by n alpha. So totally if we consider 1 plus 1 by n minus 1 alpha. Shall we write it like this? So this is for what purpose we are using? We are using for association point. Now let us analyze that dissociation concept. How do we get that formula? So here before a reaction. So how do we go for before reaction? Na equal to Nb. Here n mole it gives 0 before reaction, but after reaction it gives n mole, it gives Nb. So that means degree of dissociation, if we go for it, here minus alpha, here plus alpha. So that means 1 minus alpha, here n alpha. Am I correct for this? 1 minus alpha from 1 mole. It's reducing that alpha, so naturally 1 minus alpha, here n mole of alpha. Okay, let us add a total number of particles for dissociation. 1 minus alpha plus n alpha. Okay, rearrange this point here. 1 plus n alpha minus alpha. So, I equal to 1 plus n minus 1 alpha. Can we write it like this for dissociation concept formula? Okay, now why do we go for this point and this point? This is for dissociation. Dissociation. And this is for association. Association. Okay, now why do we require these two formulas? To analyze the number of particles only, how much number of particles it associates and dissociates in certain substance. Suppose if they are giving any substance, to analyze that number of particles, for that is the reason we are going for this formula, that is association and dissociation. Now let us go and see the sum, how to analyze it, how do we get the questions. Come on, let us go for it. See, generally dissociation means I is greater than 1 and association means I is lesser than 1. I hope you got a clear idea. Dissociation means number of particles will be more. Association means number of particles will be less, right? To combine together it will become 1. So, see, dissociation means I is greater than 1. Association means I is lesser than 1. This is the simple trick. Okay, now how to identify? These are all I factor. Definitely they will ask. Okay, HCl. How you will put it? H plus Cl minus. Here H plus NO3 minus. Here H plus 2H plus SO4 2 minus. Here H plus ClO4 minus. Right? Okay, now here the same way. Na plus Cl minus, K plus, 2K plus, SO4, 2 minus. Here, Al 3 plus, 2Al3 plus, SO4, 2 minus, 3 SO4, 2 minus. Here, K plus, 4K plus, FeCN 6 4 minus. Okay, now high factor, let us find out that I value how much? Here 1 plus 1. So here I equal to 2. Here I 1 plus 1 2. Here I value, here 2 plus 1. So I value 3. Here 1 plus 1. I value 2. I hope you got what is the value for H2SO4. How to identify also. Okay, now type of salts. This is strong electrolyte. These are all strong electrolyte. Okay, now types of salts. These are all types of salts. Okay, Na plus and Cl minus. I equal to here 2. How do we get it? 1 plus 1. Okay, now here K2SO4 for here 2 plus 1. So I value it is 3. Now here 2 plus 3. I value here 5. Now K4FeCN6. Here 4 plus 1. I value 5. Hope you got a clear idea about all these points of that association and dissociation and I factor, all those one to factor idea. Okay, now association generally dissociation value I is greater than 1 and association I is lesser than 1. This is the complete trick for these concepts. Hope you got a clear idea about all these points. Thanks for watching.